Okay, let's talk about the rest of the representations of motion tutorial. Now remember, the setup here is that there is a detector that is measuring your position and velocity and acceleration relative to that detector. And if you imagine the detector is over here, remember the coordinate system is such that position is positive in front of the detector. If you're moving away from the detector, that's positive velocity. If you move toward the detector, that's negative velocity. And in all these questions, there are 4 parts you have to fill out: a description and 3 graphs. And generally they give you information about one of those 4 and you fill in the rest. So we left off at question G, and in question G, they provide you with just the position versus time graph. So let's see what's going on here. You start out at a faraway position and gradually get closer and closer to the detector. So if you were moving relative to the detector, you would start out far at a large position, and as time progresses, move toward it and get closer. And notice that the rate that you're moving gets slower over time. Initially, you move toward the detector quickly, and then as time goes on, you move more slowly toward the detector. So with that description, we can then draw the velocity versus time graph, keeping in mind that moving toward the detector means negative velocity. So we start out with a large negative velocity at the beginning and end up with a small negative velocity at the end. So that graph would look something like this. Large negative velocity and slowing down, but always moving toward the detector. So this never actually hits 0, it's negative the whole time. And now we can fill in the acceleration versus time graph, because acceleration is just the slope of the velocity graph. And this velocity graph has a positive slope. So acceleration is a constant positive value the whole time, which makes sense because if you're moving toward the detector and slowing down means that your acceleration is opposite the direction of your velocity. So velocity is negative, that means acceleration must be positive. All right, so finally we'll write the description of this motion. You move toward the detector, slowing down at a constant rate. So that's question G. Let's move on to question H. All right, question H, they give you just a description. We move toward the detector with decreasing speed. Then, this is a long one, just as you've come to rest, move away from the detector with increasing speed. Okay, so let me just demonstrate what that motion looks like. If we imagine the detector's here, then we would move toward the detector, initially fast, and then slowing down, come to a stop, and move away with increasing speed. I think the best graph to start with would be the velocity versus time graph. So there's several parts to this motion. First part, we move toward the detector with decreasing speed. That's essentially the same motion that we just did in part G. This is part H, by the way. So we have part of the motion where you're moving toward the detector with decreasing speed. Toward the detector means velocity is negative. Decreasing speed means it's getting less and less negative. And we do come to rest. So this actually hits zero. Zero velocity is coming to rest. And then after you come to rest, now move away with increasing speed. Move away is positive velocity. And we want that positive velocity to increase. So we just continue this straight line. Now once we've drawn that, it's easy to draw the acceleration. Acceleration is the slope of the velocity. This is a line, with positive slope. So acceleration is just a constant positive value. Sorry, that's not a very good constant line, but you get the idea. And maybe most difficult is to draw the position versus time. There's going to be a key point here. Where you reach the closest to the detector you get. So you start far away, you get close, come to a stop, and then move away again. So that position versus time graph is going to look like this, like a parabola. Here's where we're moving toward, position's getting smaller, and we stop, now move away, position is getting greater. And again, the speed is large here, the speed is small here, the speed is large here again. All right, so that's part H. Let's move on to the next question. Question I. So question I is asking, how do the acceleration graphs for F, G, and H compare? And you should have noticed that for all three of those, the acceleration was a constant positive value. Constant and positive for all three of those scenarios. So is it possible to have a positive acceleration and to slow down? Absolutely. If the acceleration points in the positive direction, but your velocity points in the negative direction, that means you're slowing down, which is exactly what happens in the first part of this motion. Negative velocity, positive acceleration, you slow down as you move toward the detector. Is it possible to have a negative acceleration and speed up? Sure it is, as long as the velocity and acceleration point in the same direction. If you had negative velocity and negative acceleration, then you'd be speeding up toward the detector. Okay, next part, J. once again, they give you just the description. It says initially move away from the detector. And maintain a constant negative acceleration. Okay. Well, I think the easiest graph to draw here would be the acceleration graph. It tells you it's a constant negative value, so all we have to do for acceleration is draw a negative horizontal line there. Now let's think about the position and velocity. If we're initially moving away, that would mean that velocity is positive. And there's several ways this could go. There's more than one answer to this question. Actually, there's more than one answer to all the ones on this last page. If we initially move away, that means velocity is positive, and it's just kind of a matter of how long we're assuming this motion goes on. So let me do it like this. We start out positive. That speed is decreasing because we have positive velocity but negative acceleration, which means at some point we're going to reach zero. And let's just continue on. Where now the speed increases. Because what is going to happen here is if we initially move away with negative acceleration, you start out fast, you slow down, come to a stop, and then move toward the detector. So now we've got this negative velocity moving toward the detector. Acceleration is still negative, so your speed is increasing. And the way that might look like on the graph is that it's an upside down parabola. You start close to the detector, you move away with decreasing speed, come to a stop, and then move toward the detector with increasing speed. There are other ways to answer this. In fact, any shift of this velocity graph would be okay as long as it starts positive. Okay, let's do the next one. This is part K. Part K gives you only the acceleration graph. And acceleration looks kind of interesting. There's two times that are of interest here. So let's mark them on all these graphs. This is saying the acceleration is 0 up to a certain time, at which point it suddenly jumps to a constant positive value, and then at a later time it goes back down to 0. So let's think about what this means. When acceleration is 0, that means you're moving at a constant speed. When acceleration is positive, that means your velocity is changing somehow. And then when acceleration goes back to 0, that means your velocity is constant and your speed is constant. Now, there are several different ways you can answer this question. In fact, there's kind of an infinity of ways you can answer this question. Whatever you draw on your velocity graph, you could shift it up and down, keeping the graph the same shape, and it would still be correct. So I'll just do one possibility. I'll do maybe the simplest possibility here. Let's say we're initially moving at some small, positive, constant speed. So we're moving away from the detector at constant speed, and now this acceleration kicks in. So your speed is increasing because velocity and acceleration are both positive. And now that acceleration's over, so you continue at constant speed with whatever that maximum velocity was that you just hit. All right, so once again, you're moving away from the detector at a slow speed. Maybe I'll demonstrate this. Here's our detector. You start moving away at very slow speed, and now you accelerate and speed up, and then continue at that top speed. The whole time we're moving away, this velocity is positive the whole time, and so we sped up here because acceleration was positive and velocity was positive. So what the position graph would look like, this is kind of weird. It would start out being a line whose slope is the velocity, and then it morphs into a parabola here while the velocity is changing. An upward parabola because things are getting faster. And then you return to a straight line, but now the slope of that straight line is the slope of that parabola there, which is pretty steep by this point. Okay, so the way we would describe this is move away from the detector with constant speed. Then speed up while moving away. Then stop speeding up, but continue moving away with that highest speed you reached. Alright, so that motion's pretty complicated. And now in the last example will get even more complicated than that. Okay, part L. Part L gives you just a velocity graph. And it looks like this. Now, without thinking conceptually about what this means yet, we can easily draw the acceleration graph. Because acceleration is the slope of velocity graph. And for this segment, the slope is 0 because that's horizontal. So we have 0 acceleration. For this segment, the slope is positive. And for this segment, the slope is 0. So in fact, the acceleration graph looks the same as it did in part K. So we can just draw that without really thinking about what this means. But now for the rest of it, we have to think about what this is telling us. All right. We'll go piece by piece. At the beginning, we're moving toward the sensor, toward the detector, because negative velocity means you're moving toward the detector with constant speed. So let's just start writing that here for our description. So that covers at least this bit. Now, what happens? Actually, let me separate this into 4 parts. So first part, move toward the detector with constant speed. That's here. Second part, third part, fourth part. Okay, what's happening in that second part? We're still moving toward the detector because this velocity is negative, but the speed is decreasing. So move toward detector with decreasing speed. Slow down. And you slow down until you come to a stop. And then you start moving away from the detector because that velocity is now positive. Velocity is positive and it's increasing in speed. And finally, you reach some maximum speed as you're moving away. Continue to move away while staying at that constant maximum speed. To summarize one more time, remember, whenever velocity is negative below that horizontal axis, that means you're moving toward the detector. So you start out moving toward the detector at some constant speed, then you slow down, come to a stop. Now velocity is positive. That means you have turned around and you're moving away. Your speed increases and you keep moving away now without increasing your speed anymore, just at whatever maximum speed you've reached. And the way to draw this graph is, again, in a few segments. So first we're moving toward the detector with constant speed. So our position would be decreasing. And we keep moving toward the detector with decreasing speed, so this is going to be parabola shaped. And now we reach our closest approach and turn around and start moving away with increasing speed. So there's another parabola segment. And then we've hit our maximum speed and continue moving away. So straight line, parabola segment, straight line. Straight lines for position always correspond to horizontal lines for velocity. Parabolic curves for position always correspond to lines of constant slope for velocity. All right, so that's the last set of graphs we had to do. See if there's one more question. Oh, question M, it says, decelerate, does that indicate the sign of the acceleration? No, it doesn't. Just keep in mind, slowing down doesn't have to mean negative acceleration. Slowing down just means velocity and acceleration vectors are in opposite directions. Okay, so we made it through this lab. These graphs are challenging to explain, and if we were meeting in person, another component of this would be to actually try to duplicate these motions with that motion sensor, and that's very physically challenging to do. You guys don't have to do that this time, but I hope you ponder these graphs, ponder these descriptions, and think about the relationship between position, velocity, and acceleration, and what signs and slopes represent.